Here we have an example on an Otto cycle. An ideal Otto cycle with air as the working fluid has a compression ratio of 8. At point A has a temperature TA and mass of air equal to 1 kg. For letter A, find the pressure and temperature at the end of the heat addition process. For letter B, find the net work output, and for letter C, find the thermal efficiency. We have additional data. The properties of air at room temperature are specific heat capacity at constant pressure equal to 1.005 kJ per kilogram Kelvin. Specific heat capacity at constant volume CV equals 0.718 kJ per kilogram Kelvin. And the molar ratio is 1.4. First we identify the different processes in this cycle. Process 1 to 2 is an isentropic process or adiabatic process. The isentropic process is a thermodynamic process where the entropy of gas remains the same, which makes it reversible. The system is both adiabatic and reversible. Process 2 to 3 is an isochoric process. Process 3 to 4 is an isentropic or adiabatic process. And process 4 to 1 is an isochoric process. For letter A, find the pressure and temperature at the end of the heat addition process. The pressure and temperature here refers to the end of addition, or QH refers to point 3. So, we are asked to find P3 and T3. However, the nearest point with available given, or point 1, is 2 points away. So, we first solve some variables at a point midway between 1 and 3. Here we choose to solve point 2. Note equation for an adiabatic process, the temperature and volume ratio is given by the equation here. The volume ratio here refers to CR. So, the temperature at point 2 is about 689 K. For the pressure at point 2 or P2 in an adiabatic process, we use the ideal gas equation. Since the number of gas, Nr, remains constant, then comparing the points 1 and 2. Equating the equations. Finally, substituting the known values and getting the pressure at point 2 is about 745 kilopascals. Now we have the temperature and pressure at point 2, which we will use to obtain the temperature and pressure at point 3. To solve for the T3, we use the heat equation where it is based on the specific heat at constant volume. Rewriting this equation and substituting the known given values, we have that the temperature at point 3 is about 1753 Kelvin. Now we have the temperature at point 3, and to solve for the pressure at point 3 we use the equation for an isochoric process. Since the number of gas, Nr, remains constant, then comparing the points 2 and 3. Equating the formula and rewriting it to solve for the pressure 3 is about 4,392 kilopascals. Letter B, find the net work output. Recall the first law of thermodynamics. For a cyclic process we have the internal energy equal to 0. So the work is simplified as work total equal to heat total. The heat total is the difference of the heat input minus the heat output. The input and output simply refers to QH and QC. So, the net work is expressed as Q hot minus the Q cold. Here Q cold is still unknown, so we solve this first. To solve for QC we use the heat equation where it is based on the specific heat at constant volume. Rewriting this equation we see that temperature at point 4 is unknown. To solve this we use the equation here for an adiabatic condition at the process of 3 to 4. So, the temperature at point 4 is around 755 Kelvin. Substituting this and we get that the QC is about 327 kilojoule. Substituting the values of QH and QC back to the work total equation, we get that the work total is about 423 kJ for the Otto cycle. For letter C, find the thermal efficiency E for an Otto cycle. We get that its efficiency is about 56.4%.